redeem of that answer. So you have negative log of 0.020, 1.69. So that is the pH, right? Now, what about the pOH? What do you say pOH is? Negative log, pOH is negative log of OH. But if OH is not given, pOH is equals to 14 minus pH. Alright? 14 minus pH. So at the end of the day, this will be 14 minus 1.69, and that will give us, press it in your calculator, 14 minus 1.69 12.31. So that is the answer to that first one. Now, how about the second one? The second one, they gave you for base. So what we should be having for is the sodium hydroxide we split, my dear student, to give us what? Sodium plus OH negative, right? Now, at the end of the day, what do you think we are going to have? If 0.005 mole of sodium is reacting, it's going to give us this 0.005 based on the explanation I've given before. So this is the OH ion. What is our pOH? Negative log of what? OH negative. So you press negative log of 0.005, 2.3. So to get the pH, it will now be 14 minus pOH, right? So 14 minus 2.3 is going to give us 11.7. So that will be your pH. A blood specimen containing 7.2 times 10 to the power of minus 8 mole per liter of hydrogen ion. Is the blood specimen slightly acidic or basic? Now you have to find the pH. They gave you, this is the concentration of the hydrogen ion, right? So if you are given the concentration of the hydrogen ion, how do you get the pH? You know pH is minus log hydrogen ion, which is 7.2 times 10 raised to the power of minus 8. Alright, so you have minus log 7.2 times 10 raised to the power of what? Minus 8. 7.14. So we can say that the blood specimen is slightly basic, because we said exactly 7 is neutral, less than 7 is acidic, greater than 7 is what? Basic. So it is slightly basic. Blood samples are usually slightly basic as compared to what? Acidic. Alright, good. Now, so that is that for that question. Now, 0.0, where this compound has to be considered to be 100% dissociated. Calculate the pH and the pOH. You can calculate the pOH of this one now. 14 minus this value to give you the pOH. So this one is barium hydroxide. So writing the equation of dissociation, this is going to give us barium 2 plus OH negative, but you have 2 OH negative here to balance this equation. Alright, so if 0.00035 of barium dissociate completely, it means 0.0035 of barium ion will be formed, and 2 times 0.00035 of hydroxyl ion will be formed. So you are now going to press negative log of 0.00035 times 2, 3.15. So your pOH here, you know what I just did now? I got this multiplied by this will give us our OH. To get the pOH, negative log of this, which will now give us 3.15. To get the pH to be 14 minus 3.15, and then 14 minus 3.15 minus 14 going to give us 10.85. 10.85. All right, so that is a correct answer to that question. Is that okay? Good. Now, so that is that. Now, in this lecture, we are going to consider the relationship between pKa, pKb, and pKw. Now, they are going to give you a question like this in the exam. Now, the question will say, using acetic acid, show the relationship between pKa, pKb, and pKw. Using acetic acid, show the relationship between pKa, pKb, and pKw. Now, how do you solve this kind of question? Now, of course, you can see in your screen here, it said consider an aqueous of, supposed to be an aqueous solution of ethanoic acid. Now, when ethanoic acid is dissolved in water, we said that the ethanoic acid will donate its proton to water. When it donates its proton to water, water will become protonated to form the hydrozonium ion, which is the only positive ion as postulated by the Arrhenius definition of acids. And then you are going to have the acetate ion here. All right. Now, if you write the equilibrium constant expression for the acid, or the acid dissociation constant, Ka, you agree with me that Ka would be equal to the concentration of the products all over the concentration of the reactant following the law of mass action. So in this case, you are going to be having the concentration of the product all over the concentration of the reactant, as you can see on your screen. Like I told you, that when you are writing the equilibrium constant expression, pure solids and pure liquids do not usually show in the equilibrium constant expression. Is that okay? Pure solids and pure liquids do not usually show in the equilibrium constant expression. Is that fine? Alright, so pure liquid and pure solids do not show in the equilibrium constant expression. So you are not expected to see water in the equilibrium constant expression. Is that okay? Why? Because we said that their concentration do not change during the course of the reaction. Of course, everybody know how to write Ka by this time. Now, consider an aqueous solution containing the ethanoic acid, which is the conjugate base of ethanoic acid. So if you have an aqueous solution containing the ethanoate is the conjugate base of ethanoic acid. Of course, at this point of this lecture, every one of you should understand what the conjugate base is all about, right? At this point of this lecture, you should be able, or you should understand what the conjugate base is all about. Now, you agree with me that this one here is a base and the H2O is the acid in this case, because you already be told that this guy here is what? Is a base. Are you getting it? This guy here is a base. Hence, H2O is the acid. So, it means that H2O will protonate the base by giving it what? Its proton. So, when H2O protonates this base, it means one hydrogen ion will come here to form acetic acid plus what? Hydroxide ion, which is OH negative. Now, because you are actually considering this acetate ion, which is a base, you now say this is Kb, which is the base dissociation constant. Of course, the base dissociation constant gave you this and this, right? Now, at this point in time, what do you think we can actually do now? What we can do is, you already have the expression for Ka as this. You already have the expression for Kb as this. You want to show the relationship between pKa, pKb, and Kw. Now what are you to do next? Is very easy. Now multiply Ka and Kb. You have the value of Ka, you have the expression for Ka rather, which is this. So write that here, which is what you have here. We have the expression for Kb, which is this, and this is written here. So that at the end of the day, you multiply them. Now when you multiply them, ethanoic acid will cancel ethanoic acid. Acetate will cancel acetate. So what are we left with? We are left with hydrozonium ion and hydroxide ion. So you can now see that Ka times Kb is equal to hydrozonium ion times hydroxide ion. Of course, we also postulated earlier on that our Kw, which is the acid dissociation constant, is equal to hydrogen ion multiplied by hydroxide ion. Hydrogen ion is still the same thing, it's equivalent to what? Hydrozonium ion. So it means that this entire stuff you have here, hydrozonium ion multiplied by hydrogen ion, hydroxide ion, is still the same thing as what? Kw. So we can say that Ka times Kb is equals to what? Kw. Alright? So if we say Ka times Kb is equals to Kw, you are now having Ka times Kb is equals to Kw. Now taking negative logarithm of both sides, you are now going to have minus Ka. That means you multiply through by minus Ka. Now in that case, you are now going to have minus Ka plus minus log Kb is equals to minus log Kw, because we said we are multiplying everything here by negative logarithm. Of course, every one of you know that minus Ka is equivalent to what? Pka. And minus Kb is equivalent to what? Pkb. Do you understand? Which is equals to minus log Kw is equivalent to what? Pkw. Let's take it again. Minus log Ka is equivalent to Pka, minus log Kb is equivalent to Pkb, and minus log Kw is equivalent to what? Pkw. Is that okay? Now, do you know the reason why this multiplication was changed to addition? That is where the knowledge of your mathematics comes in. According to law of indices, when you are using log to multiply through and there is multiplication in the middle, that multiplication changed to what? The positive. That is why you have this positive sign here, in case you don't really understand what we have by that. All right, now that is that. So at the end of the day, you are now having Pka plus Pkb is equals to Pkw. So that is one. Now you have an example here. Say calculate the pH of a 0.10 mole solution of sodium ethanoate. Ka for ethanoic acid is 1.8 times 10 raised to the power of minus 5 mole per dm cube. Now at this point in time, what do you do? It's very easy, but then we have to solve it. Let me see. Watch your screen. Watch your screen. What is wrong with this one? All right, so let's solve this question. It's a very simple question. Now, this is one of the exam questions that have subsequently repeated itself, or this is one of the exam questions that have been repeated subsequently. Now the question says, calculate the pH of a 0.10 mole dm cube solution of sodium ethanoate. Now the Ka was given to you, but the Ka given to you was the Ka for acetic acid, which was given as 1.8 times 10 raised to the power of minus 5 mole per dm cube. Now, you are asked to calculate the pH of sodium ethanoate. Now, what is the reaction of sodium ethanoate? Now, according to what you know, you agree with me that you said sodium ethanoate, here is this stuff, it's supposed to be white. Alright? Now, sodium ethanoate, which is something like this, according to what I told you, will react with water in a reversible reaction. This water will donate a proton here, so that it will now give us ethanoic acid plus hydroxide ion. Now, what was the Kb, the base dissociation constant? We are told that Kb would be equals to the concentration of the product, all right, OH negative, divided by the concentration of the reactant, except of course the concentration of water, which is a pure liquid which does not change and hence does not show in the equilibrium constant expression. All right, but we are not giving Kb, but we are giving Ka. Ka for acetic acid, you must bring out your parameters like this, was given as 1.8 times 10 raised to the power of minus 5 mole per dm cube. So we must have the value of what? Kb in order for us to solve this question. Now, Ka was given as 1.8 times 10 raised to the power of minus 5 mole per dm cube, my dear students. Now listen, but we know that Ka times Kb is equals to Kw. What is the value of Ka? 1.8 times 10 raised to the power of 5 times Kb. Kw is 1.0 times 10 raised to the power of minus 14. Is a constant. Every one of us know the value of Kw. Kw is a constant. Is that okay? Kw is a constant. You know the value of Kw. Kw is a constant and the value is 1.0 times 10 raised to the power of minus 14. So that at the end of the day, when you now divide both sides by our value there, divide both sides by 1.8 so that we can have our Kb times 10 raised to the power of minus 5, divide by 1.8 times 10 raised to the power of minus 5. This cancel this. Kb would be equals to, when this divide by this, what are you going to have? Have 1.0 times 10 raised to the power of minus 14 divided by 1.8 times 10 raised to the power of minus 5, which will give us 5.56, let's approximate it, times 10 raised to the power of what? Minus 10. So this is our Kb. Is that okay? This is the value for our Kb. It's very, very important we take note of this. Now, but we have the expression for Kb. What was the expression for Kb we have? We said Kb is equals to this, right? Now, this ethanoic acid is a weak, the ethanoate rather, when it dissociates, it gave us something like this. Now, the concentration of ethanoate that dissociates, was it given in the question? They say the pH of 0.10 mole per dm cube of sodium ethanoate. Is that okay? That is that. That was what was given. Is that okay? But then we need to actually calculate the concentration of OH negative. Now you started with 0.10 mole per dm cube of ethanoate. Is that fine? Now at the end of the day, there is something we must know. Ethanoate itself is a strong base, and because it's a strong base, it dissociates to a very large extent in solution. Is that fine? So how do we solve a question like this? It's very easy. Now sorry about that. Acetate ion, which is sodium ethanoate, is a weak base, or is a base, right? Now since it has a dissociation constant, that means it's partly dissociate in water. Not all of them does not dissociate completely in water. Hence you can say it's also a weak base. Now my dear students, what do we do now? Let's take it to the equilibrium constant expression. From what we know, we said acetate ion plus H2O to give us this. Now, initially, what is the amount of acetate ion given in the question? Before I say acetate ion, sodium ethanoate, rather, 0.1 mole per dm cube of sodium ethanoate. Is that okay? So we can come here and impute it and solve with that. So 0.1 mole So we can say at the initial time the reaction started, here is 0.1 mole per dm cube. All right, exactly. Now, but as time progresses, initially here will be 0, here will be 0, but as time progresses, this one will lose a portion of it, so we have 0.1 minus x, right? Y here will be x, y hydroxyl ion will also be x, based on what I've taught you before. I've taught you something like this, a similar question like this. So at the end of the day, we know that our Kb initially is what? CH3 COOH, then bracket what? OH negative divided by CH3 COO negative, which is the acetate ion. Now at the end of the day, what was our value for Kb we calculated? It was 5.56. So in place of Kb, we put 5.56 times 10 raised to the power of minus 10. The acetic acid, now if you look at it, we can say it's X. You already know, I already explained something like this before, right? So you know where this X and this X are coming from. Told you that a percentage of this actually dissociated, so it's going to form S% of this and X% of this. So we have X times X divided by, here will be 0.1 minus X. But we said that this X that actually left, that was dissociated, we can neglect it because the value is what? Negligible compared to the 0.1, right? So this value here will be approximately 0.1. So what do you think we are going to be having, my dear student? You are going to be having, this is supposed to be, sorry about that, 5.56. So here will be 5.56 times 10 raised to the power of minus 10 is equals to X times S will give us what? S square divided by 0.1. Now at this point in time, cross multiply. S times 1 will give us what? S square is equals to 5.56 times 10 raised to the power of minus 10 times 0.1. Alright, so at the end of the day, we are going to have S square. When this multiplied by this, my dear students, think it's going to give us 5.56 times 10 to the power of minus 10 times 0.1. Supposed to give us times 10 to the power of minus A? No, 5.56. Alright, so at this point in time, we can now multiply this. I think it's supposed to give us 5.56 times 10 raised to the power of minus 11. Right? This times 10 raised to the power of minus 10 times 0.1, which is 5.56 times 10 raised to the power of what? Minus 11. So X will be the square root of 5.56 times 10 raised to the power of minus 11. So that at the end of the day, X, the square root of answer, so that will give us sorry about that, 7.456 times 10 raised to the power of minus 6. So that's our X. Now recall that X is still sitting as what? The hydrozonium, the concentration of the hydrozonium ion, right? So it means the hydrozonium ion, my dear students, concentration is 7.45 times 10 raised to the power of what? Minus 6. That's the hydrozonium ion concentration. And if you check back to where we are currently in the material, you agree with me that we are in line with what is in the material. OH ion is 7.45 times 10 raised to the power of minus 6. So we need to calculate for the POH. How do we calculate for the POH? We already have the OH concentration. So to get the POH will be negative log of OH negative. So POH will be minus negative log of 7.45 times 10 raised to the power of what? Minus 6. Is that okay? So therefore POH will be, you press that in your calculator, minus log 7.45 times 10 raised to the power of minus 6. That will give us 5.12. 5.13 approximately. So that is the POH. Now, what you are going to do for me is to tell me the pH. We already know the pH. How do we get the pH? Every one of you know how we can get the pH, right? Let me erase this part of the board so that we can solve here. How do we get the pH? Have we gotten the POH? Now we can say that POH, for what we know, plus pH is equals to 14. So pH will be 14 minus the POH. Now the POH is 5.13. So pH now, 14 minus 5.13, what are you going to get? Minus 14, that will give us 8.87. So that's basically how they got these answers you can see here. Aren't it? Is it not very easy? 8.87. You can see it here. All right. So that's how they got that answer. All right. So let us talk about the next, which is acid-base titration. Now, what is the purpose of acid-base titration? You already did this before your first semester. Everything concerning the acid-base titration. Now the purpose is to determine the volume of two solutions, acid and base, which exactly neutralize each other. That is the reason for acid-base titration, most especially to assay compounds. Is that okay? That is the purpose of acid-base titration, to assay the purity and to actually standardize different solution. Now most acid and base and salt are colorless in water. Therefore, an indicator is necessary to pinpoint the endpoint of the titration. Now, this is something that you guys can actually read and understand. Substance which change color according to the pH of solution to which they are added, those are called indicator. Now, you have the different indicator, their color in acid and their color in base. You have phenolphthalein, in acid is colorless, in base is purple. Methyl orange, in acid is red, base in is yellow. Methyl red, in acid is yellow, in base it is red. Now equivalent and endpoint. Now the equivalent point is when the amount of acid and base present exactly neutralizes one another. At this point, neither acid nor alkaline are present in excess. So in a situation where the amount of acid and base are exactly the same and they neutralize it, not exactly the same, but the point at which they neutralize each other, that there is no base nor acid, at that point where only salt and water is formed, is called the equivalent point of a titration. Now the end point of titration is when the indicator changes color. The equivalent point is different from the end point. When the indicator changes color is the end point. The indicator must change color at the equivalent point, not before or after. The indicator must change color at the equivalent point, not before or after. Now we have different indicator and what they are suitable for, or different titration processes and which indicator should be used for such titration in order to get accurate result. Now we have the strong acid plus weak base. This is something that is in your secondary school Ababio chemistry textbook. Strong acid and weak base, the indicator that is suitable is methyl orange. Weak acid, strong base, phenolphthalein should be used. Strong acid, strong base, either methyl orange or phenolphthalein should be used. And the weak acid plus weak base, no suitable indicator is required. Now that is that for this particular one. Now the next lesson is salt. Identifying the type of salt, how to calculate the pH of salt, define examples of buffer, identify the type of buffer, calculate the pH